Identification problems plague empirical analysis in many areas of science. And what I've shown in this lecture is that when models are not identified, that undermines our ability to draw causal inference from the observed data. And if we leave them uncorrected, it can actually lead highly misleading results, as we've just seen. A key source of non-identification arises due to confounding, which can actually be hard to detect and hard to treat. If we want to know about causality and confounding, domain knowledge and theory informs us about the causal structures embedded in the data generating process, and it therefore provides guidance on covariate inclusion, which covariates to include in the model. I hope what this lecture has also shown is that good data, access to good data, helps enormously when we're trying to estimate causal inference. The potential outcomes framework provides a non-parametric mathematical model that allows us to derive the conditions required for causal identification. And what it's said is that there's a thing called the conditional independence assumption. It really just says that we have to adjust for confounding influences. That's how we achieve identification. We then went on after identification to look at how this principle is applied in estimation. We looked at outcome and regression and propensity score estimators for settings in which the CIA holds, and we looked at instrumental variables for settings in which that assumption fails. And if we had more time in this course, we would go on to look at other causal estimators that allow us to get round the CIA, and that includes regression discontinuity design, difference in difference, and synthetic control. Effective use of all of these causal methods requires us to really understand the assumptions underpinning identification and how these relate to the nature of the underlying estimation problem, so to the data and to the estimand that we're actually trying to estimate.